x86S is a proposed architecture design by Intel that aims to simplify the Intel 64 architecture by removing some of the legacy modes and features that are no longer used by modern software. Intel believes that this simplification can reduce the complexity and improve the performance of the hardware and software ecosystem. Intel 64 architecture has evolved from the original 8086 processor that was introduced in 1978. It supports various modes of operation, such as real mode, protected mode, virtual 8086 mode, and long mode. These modes allow backward compatibility with older software and operating systems, but they also add overhead and complexity to the architecture. Intel argues that most of these modes are not needed in modern applications or operating systems, which run exclusively in 64-bit mode. For example, Windows 11 is a 64-bit only operating system that does not support 16-bit or 32-bit applications natively. Therefore, Intel suggests that some of these modes could be removed to create a 64-bit mode-only architecture that is simpler and more efficient. x86S is the name that Intel gives to this 64-bit mode-only architecture. It stands for x86 Simplified. According to Intel's white paper, x86S would eliminate some of the legacy features of the Intel 64 architecture, such as real mode and virtual 8086 mode, which are used to run 16-bit software, protected mode, which is used to run 32-bit software, Ring 1 and Ring 2, which are unused by modern software, segmentation features, such as gates and descriptors, string port I/O, which is an obsolete CPU-driven I/O model, local APIC support, which is replaced by X2 APIC, some unused operating system mode bits. By removing these features, x86S would simplify the booting process, the paging mechanism, the memory management, the interrupt handling, and the instruction set of the Intel 64 architecture. This could lead to faster and more secure systems in the future. Intel claims that x86S would not affect the compatibility with existing 64-bit software or operating systems. However, it would require some modifications to the firmware and the operating system kernel to support the new architecture. Moreover, it would prevent running older software or operating systems that rely on legacy modes or features. For those cases, Intel suggests using virtualization-based solutions that can emulate the required features. Intel is currently investigating the feasibility and benefits of x86S as a future direction for its processor architecture. It is seeking feedback from the ecosystem while exploring the possibilities of extending the ISA transition to a 64-bit mode-only solution. In this section, we will explore the benefits of x86S architecture for hardware, firmware, software, and performance. x86S is a proposed 64-bit mode-only architecture that simplifies the Intel ISA by removing some legacy modes and features that are not used by modern operating systems and applications. Intel published a white paper detailing the architectural enhancements and modifications that they are currently investigating for x86S. One of the main benefits of x86S is that it enables a faster and simpler booting process for the CPU. Today, Intel 64 architecture designs come out of reset in the same state as the original 8086 and require a series of code transitions to enter 64-bit mode. This involves switching from real mode to protected mode to long mode, which adds complexity and overhead to the firmware and software. With x86S, the CPU would start directly in 64-bit mode, eliminating the need for trampoline code and legacy mode transitions. Another benefit of x86S is that it reduces the hardware complexity and improves the security of the system. By removing unused features such as Ring 1 and 2, string port I/O, local APIC and legacy 8259 support, x86S simplifies the segmentation model and the interrupt handling mechanism of the CPU. This reduces the hardware area and power consumption, as well as the potential attack surface for malicious software. Moreover, x86S eliminates support for Ring 3 I/O port accesses, which are a source of privilege escalation vulnerabilities in some operating systems. A third benefit of x86S is that it aligns better with modern software deployment and development. By removing 16-bit addressing support and obsolete segmentation features like gates, x86S eliminates some compatibility issues and performance penalties that arise from running 32-bit applications on 64-bit operating systems. Furthermore, x86S enables a smoother transition to 5-level paging, which is a feature that allows addressing more than 256 terabytes of physical memory and more than 128 PB of virtual memory. Today, using 5-level paging requires disabling paging, which requires going back to unpaged legacy mode. With x86S, it would be possible to switch to 5-level paging without leaving a paged mode. In summary, x86S architecture offers several benefits for hardware, firmware, software, and performance by removing some older appendages of the architecture that have little utility in modern systems. Intel is still investigating the feasibility and impact of x86S on the ecosystem, and is seeking feedback from developers and users while exploring this 64-bit mode-only solution. Possible script: what are the challenges and implications of x86S for legacy support and compatibility? As we have seen, Intel's x86S architecture is a proposal to simplify the x86 instruction set by removing some of the legacy modes and features that are no longer used by modern software. This could bring some benefits such as faster booting, reduced complexity, and improved security. But what are the challenges and implications of this transition for legacy support and compatibility? One of the main challenges is how to run older operating systems and applications that rely on the legacy modes and features that x86S would eliminate. For example, some operating systems may need to use real mode or protected mode during booting or switching to 5-level paging. Some applications may use 16-bit addressing, segmentation, or port I/O. These software components would not be able to run natively on x86S processors. Intel suggests that there are two possible solutions for this challenge. One is to use virtualization-based software solutions that can emulate the legacy features required by the older software. For example, using virtual machines or hypervisors that can provide a virtual x86 environment with all the legacy modes and features. Another solution is to use dedicated hardware for running legacy software, such as older PC systems or specialized devices. Another challenge is how to ensure compatibility and interoperability between x86S and existing x86 processors and platforms. For example, how to handle binary compatibility, instruction encoding, exception handling, memory management, interrupt handling, and system management. Intel proposes that x86S processors would be backward compatible with existing x86 binaries, but not forward compatible with x86S binaries. This means that x86S processors could run existing x86 software, but not vice versa. Intel also proposes that x86S processors would use a new instruction encoding scheme that would allow them to coexist with existing x86 processors in a heterogeneous system. The implications of x86S for legacy support and compatibility are significant and require careful consideration and collaboration from the hardware and software ecosystem. Intel is currently investigating the feasibility and benefits of x86S architecture and soliciting feedback from the industry while exploring the possibilities of extending the ISA transition to a 64-bit mode-only solution.